To get started, download and open the provided model in Ansys Discovery and make sure you are in the Explore mode. Once you have opened the model and unhidden all the components, click on the triad for the car cabin volume to open it. Since we only want to include the main fluid volume in our simulation, right-click on the car cabin volume and select Simulate on Selection Only. Let's set up some boundary conditions. We are going to apply an inlet mass flow rate of 0.01 kg per second for both the top and bottom vents. To apply fluid boundary conditions, go to the Simulation tab and click on Fluid Flow in the Physics section to invoke the fluid flow boundary conditions heads-up display or HUD. From here, choose the fluid flow inlet boundary condition and then select mass flow rate from the right side of the HUD. Enter a value of 0.01 kg per second and hit enter or click on the check mark to apply the same boundary condition. Let's repeat the same process for the other two vents. After applying fluid flow inlet boundary condition, let's apply 0 Pascal pressure outlet boundary condition on this phase. To do this, select outlet from the left side of the fluid flow HUD and then choose pressure from the right side of the HUD if not selected by default. Set it to 0 Pascal and hit enter or click on the checkmark icon to apply the same. Since our geometry is symmetric in nature and we are using quarter of the original car cabin for this tutorial, we need to apply a symmetry boundary condition on this symmetric face. To do this, click on Symmetry under the Simulation tab in the Physics section, then click on the symmetric face, hit enter or simply click on the check mark to apply the symmetry boundary condition. To set all the other solid components to be cutter bodies, right-click on the volume component inside car cabin volume from the model tree, then click on the overlapping bodies option and select set to be cutter bodies. You can cross-confirm that all the other overlapping bodies are set as cutter bodies by looking for a minus sign on top of the components icon. If you want to remove any body from the cutter body, right-click on the component you want to remove and unselect cutter body to remove the same component. To capture the inlet faces and vents more efficiently, let's apply some local fidelity. To apply local fidelity to inlet faces, Control select all the inlet faces and click on Local from the Fidelity section under the Simulation tab. Enter a value of 5 millimeters and hit enter on your keyboard to apply the same. We can confirm that the local fidelity settings have been applied by hovering our mouse cursor over the fidelity adjustment settings in the physics tree, and it will highlight the areas where we applied the local fidelity. To apply local fidelity to the vents, first unhide them from the model tray by clicking on the eye icon and then hide the other bodies. Then click on Local from the Fidelity section under the Simulation tab. Do a box select on all the vents to select all the faces. Since you have selected all the faces on all the vents, enter the value from the left side of the HUD and apply a local fidelity of 2.5 mm. Cross-check whether the local fidelity settings have been applied to the correct location by hovering your mouse cursor over the fidelity adjustment settings. Now that we have set up the simulation, let's solve it. The solution is complete. Let's review the results. First, turn off the vectors by clicking on the vectors icon in the result arc. Then turn on the contours from the result arc and set the location to all bodies by right-clicking on the contour icon and changing the location from all faces to all bodies. Set the slider bar from the legend to adjust the flow range. Set the top slider position to the maximum velocity and the lower slider position to somewhere between 1 to 2 meter per second. To see the high velocity gradient flow, you can observe that the flow is coming out of those vents in an expected manner. Let's try to rotate the top vents to see how the flow changes. Select one of the top ball vents from the geometry tree. Invoke the Move tool by pressing M on the keyboard or by going to the Design tab and clicking on Move in the Edit section. Rotate the vents a little bit. The moment you rotate the geometry, the solution starts again, and you can observe the flow changes based on the rotation. By using cutter bodies, you just saw how we can Boolean the solid bodies from the bulk fluid region on the solver level, and you don't have to deal with any defeaturing or performing any extra operation like subtracting the solid from the fluid region.